projectiles, and I'll do it through a few examples. Basically, we treat projectiles just the same as doing SUVAT questions. The key thing to note is we treat an object as a particle, so the only force acting on it is its weight. So that means horizontally there's no force acting, so we have no acceleration, but vertically we have all the force acting, and it's just weight, so the acceleration is the gravitational constant, which is usually 9.8, but because when we're thinking of travelling upwards, it's going to be negative 9.8, but there are some exam questions which use a different number, so you have to read carefully. Right, so we'll try a couple of questions. So this first one, for every question, what I do is sketch a picture of what's going on. It's particularly important if we don't start from the ground. In this question, we do start from the ground. So here's some ground. Okay, here's my ball. I'm going to kick it, and then it's going to travel up in the air, and so on. So the ball first hits the ground a distance of 60 meters away. So we know that this distance here is 60 meters, okay? Says it sets off from a point O on the horizontal ground. And the time of flight, so I'm just going to write, the time of flight is 4 seconds, so I'll keep myself organised. The motion of the ball is modelled as a particle, so we can do our projectile stuff, moving freely under gravity. Find the horizontal and vertical components of the initial velocity of the ball, okay? So we want the initial velocity. I've drawn a picture. Now what I do for all of my questions is write out SUVAT and then fill in the details. So in the I direction, so horizontally, we know that we have got a total distance of 60 meters. Okay. We don't know what our initial velocity is. So I'm going to call my horizontal initial velocity, I'm going to call that ux. And my vertical initial velocity, uy. Okay, so there's ux. We know that our final velocity is going to be the same, so we don't care. We know there's no acceleration due to gravity going horizontally. So the only other thing we've got is our time, which we know takes us 4 seconds. Okay, so that's the u direction. We look in the j direction now. So in the j direction, we have got a height back to 0. We've gone up, but we've gone down again, so our displacement is 0. Vertically, we've got an initial velocity, we've called it uy. We don't know anything about the final velocity. We do know that we're using acceleration due to gravity is minus 9.8. And then we've got time 4 seconds again. Okay, so draw a picture, write out SUVAT, 1 column for the x direction, 1 column for the y direction. Now it's easy. You've got your equations on the front of the paper. The only one that's useful horizontally is just that displacement is equal to velocity times time, because we have constant velocity there. So let's put our numbers in. So this is in the I direction, so we've got 60 is equal to ux times by 4. Well, that's easy. We've got our initial horizontal velocity is 15 meters per second. Okay, so that's one answer. And now we want to look in the vertical direction. So from the front of your exam paper, where your formulas are, you've got S is ut plus a half at squared. I know I'm going to use that because I've got S, U, A and T, and that's the only equation that uses those and excludes V. So then I put my numbers in. So I've got 0 is equal to uy times by 4 plus a half times minus 9.8 times 4 squared. Okay, and if you work that out, I think you get, to work out what that is. So uy is going to equal, lost my piece of paper. I haven't got it soon. No. So I feel like we've got to start again. 19.6.
Yay!
Meters per second. Okay, so that's the initial vertical velocity. Right, so we'll carry on with this question. We now have got the And we're told that the ball clears a vertical post, okay, at a height of h, and that's 15 metres from the origin. So let's have a little picture of that. There's our ground, there's our projectile, here's our origin where we set off. We now know that this velocity here consists of this component, which was 15, and this component, which is 19.6. Okay, we have got a wall there, and we know that the distance horizontally to the wall is 15 metres. So what we want to find out is what its height is. Okay, so we're interested in our particle passing here. So we're going to imagine, we're going to assume that the wall is infinitely thin, essentially all the front edge of it is, and that we're going to graze the top of that wall. Okay, so as before, we've done a sketch. We write suvat out, and we put horizontally, and we also put vertically. So I'm going to just move my 15 metres there so I can fit it in. Okay, so horizontally we're going 15 metres along. We know that our initial horizontal velocity is 15 metres per second. Okay, we know it's the same vertically, we know the acceleration is 0, and we don't know how long it takes. Okay, so now we do the same vertically, so we've got a height of h, and we started off with 19.6 metres per second. We don't know what the velocity will be as it passes that point. The acceleration is going to be that due to gravity, so minus 9.8, and we've got time t. Okay, so again, it's the same equations. We've got s equals u plus ut horizontally and vertically, s equals ut plus a half at squared using these things. So let's write those out. Okay, well that's really helpful because it now tells us what our time is going to be. So it's going to pass the wall at 1 second. Okay, we can use that to help us in the next equation. So we put our numbers in. H, which is what we're interested in, is 19.6 times 1 plus a half times minus 9.8 times 1 squared. Okay, and that gives us 14.7 metres, which is what we're required to get. Okay, so that was quite nice. We then want to find the speed of the ball as it passes over that point. Okay, now notice it says speed, so we've got to watch out for that. It didn't say velocity. A velocity is a vector. Speed is going to be the magnitude of that vector. So we want to know the two components of the velocity at this point as it's passing over the ball. So we need this one here and that one there. And once we've got those, we can combine them to get the speed. Okay. Right, so I'm going to just add to this bit here, so I know that this is also 15, because horizontally we have no acceleration, which means our final velocity is exactly the same as our starting velocity. So we've already got what we need for our triangle for that. So I'm going to just dot over here. This is for part 3. I'm going to draw myself a little triangle. Okay, so we know that that's 15 metres per second. Going horizontally. Right, what about vertically? So let's put V in here. So now we know that time is 1. I'm going to use my favourite equation. We can use any of the equations from the front of your exam paper that include V. So I'm going to use my favourite, which is V equals U plus AT. I like it because there's no squares. Okay, so we put in 19.6 times 1 plus minus 9.8 times 1, and if we do that, we get our velocity being 9.8 metres per second. Okay, so now we've got that here, 9.8. So we're after this length here, so we can use Pythagoras. So we want the speed, which we know is the magnitude of the velocity. Okay, oops. So that's going to be the square root of 15 squared plus 9.8 squared, and we end up with 17.9 metres per second. Okay, right, this question has got one last part, which is a short and sweet bit. Oh no, two last parts. Okay, so measurements show that the speed of the ball as it passes over the post is in fact not equal to this value that we found. Okay, state a deficiency of the model that might account for this. So if we went back to the very beginning, we'd see that this motion of the ball is modelled as that of a particle moving freely under gravity. So it means that the only force acting upon it would be weight. So a deficiency of the model is that it hasn't included something like air resistance, which is usually the most obvious. So all you need to do is state that it doesn't include air resistance. And then explain whether an improved model would require a larger or smaller initial value for the speed for the ball. Okay, so if we have air resistance, that's going to be acting against the direction of motion, so it's going to slow us down. So if we want to still clear that wall, we're going to be going slow. We're going to have to start off with a faster initial speed. Okay, so we need a larger initial speed so that we can deal with that air resistance and still get over the wall. Okay. Right.